Assalamu alaikum. I'm Ibrahim Musa and I'm here to teach this Telikilaas grade 10 physics lesson. In today's lesson, we are going to do some revision work based on what we have studied under circuit components and logic gates in the previous Telikilaas lessons. Before we proceed, first look into the objectives of the lesson. So by the end of the lesson, you should be able to confidently do questions on logic gates and circuit components. Let us first recall, before doing some questions, let us first recall what five logic gates that we are going to study. That is O, AND, NO, NAND, and NOT gate. As you can see, each and every gate, it is having an inputs and outputs. So which means based on an input, which is input signal, which is given to a gate, it creates a specific type of output. So that's how a logic gate works. In an OR gate, it has two inputs, which is input A and B, and then it creates an output here. So in an OR gate, if an input is there at A or B, in any of it, it will create an output. But when we talk about a NOR gate, if it is having an input at A or B, then it will not create an output. When we talk about an AND gate, when there is an input at A and B, it will create an output at B. So output at C. So it has to have an input at both A and B in order to create an output at C. The NAND gate is the opposite of this. If it is having an input at A and B, it will not create an output here. When we talk about the NOT gate, which is the most unique one here, if it is having a single input and a single output. So how does the NOT gate work? So the NOT gate, if it is having an input, it will not give an output. But if it is not having an input at A, it will create an output at, sorry, it's a B. So in logic gates, we are going to refer the values in terms of ones and zeros. We call these the binary numbers, or maybe it can be referred to as on and off. So an on is referred to as 1 and an off we can refer to as 0. So either way you can explain it. Let us look into the very first question of today's lesson. So the question says, in the space below, write down the truth table for a NAND gate. Okay, so this is interesting. So a NAND gate should look like this. Two inputs. It is going to have two inputs and a single output. So how does a truth table look like? The truth table, so we are going to have three here. So the first one is going to be A, B, and C. So this is going to be input A, this is input B, and this is going to be the output here. So if both A and B is having an input, it will not create an output. So which means if it is having an input at A and B, it should not create an output. Okay, so we will continue the truth table. If it is having a 0 here, and then if it is having a 1 here, then it will create an output. If we are having a 1 here, if it is an input here and no input here, it will still create a 1, an output. And then if it is not having an input here and here, it will still create an output. So it's the complete opposite of AND gate. So the second part says in figure 10.2 shows connections to two logic gates. Okay, so this is interesting. Here, as we can see here, this is an OR gate, and then we have an AND gate here. So what you need to understand is at the OR gate, any of A and B can have an input to create an output at D. And then for this AND gate to work, both the D and C should have an input to create an output. So the next question says it shows a part of the truth table. So here we have the truth table here, and the same question, same diagram I have. Then we'll move to the next part of the question. So here we have the truth table here, and the same question, same diagram I have placed there. So you're supposed to complete this truth table values. So this intermediate value D here, I mean D is there. So in order to get the values for the for D, you need to consider values of A and B. So this is an OR gate. So how does an OR gate work? In order for a OR gate to work, it should have an input at either A or B. Any can have an input. So in the first scenario, we don't have any inputs here, which means there is going to be no output at D. In the second scenario, we have an input at B, but no input there, but that is fine because this is an OR gate. OR gate will give an output if there is any input at any A or B. And in the next two scenarios, in the third and fourth scenario, we have inputs at both A and B, which will give us an input here and here. Now, when we try to find the final output for E, then you need to consider both C and D because two inputs are C and D for the AND gate here. So, and in order for an AND gate to work, it should have an input at both D and C. Now, in the first scenario, when we look into this, it's in the first scenario, we have a single input. We have an input at C, but no inputs at D, which means there is going to be no output at E. In the second scenario, we have inputs at both C and D, which means it will give an output at E. In the third scenario, we don't have an input at C, but we have an input at D. But since this is an AND gate, both the inputs should have a value. Both the inputs, it should be on. But since that is not the case, we will not get a value here, so it will be off there. In the fourth scenario, we have inputs at both C and D. So yes, we will have an output there. Now, when we look into the second question says a student is designing a digital electronic circuit, and figure 2.1 shows her partly completed design. So as the question says, this is a partly completed design, and we already have two gates here. One is a NAND gate, and then we have a NOR gate here, and we have a total of two inputs here, so an interchange is taking place. So instead of having separate inputs for both independently, so it's interchanged there. So it has both inputs are connected somehow. And then we have an output of O. So let us read the question furthermore. So in table 2.2 is a truth table. So you're supposed to complete the columns in the truth table to show the values of input in the circuit. So we have an input A and input B, which is creating an output at C and D, and then something is there in between, and then the final output created, the values are mentioned there. So how does this actually work? So we have an input. Let us start from the very first. We have, I think in this situation, it will be easier to go backwards at some points. We have a NOT gate. Sorry, we have a NO gate here, which means NO gate means, so both inputs, it should not have any value at both A and B to create an output. So in order to get a value for C here, we have an input at B. So when we go back, the value here, it has to be 0 here. So no inputs here, giving a value, giving an output at C. Now when we go to the second one, second scenario, let's say, let us focus on the first set of value here. We have an input at A. Yes, we have an input at A, and it is creating an output at C. But in this scenario, we have an AND gate here, so it does not create anything. So if it is having any value at B, it should not create a value at C. And then when we talk about the situation at the output D, it should have values at both, so that you get an output at D. So we will have a value 0 here. Now when we talk about this value, we have outputs are creating 0 and 0 here, but in this situation we have an input here, but we don't have an input at A, but it should have an input at B, so that it does not create an output at C, and it cannot create an output at D as well. Now, when we talk about the next scenario, we have the third one. Uh, we have an input at A. We don't know this value, but it does not create. It does create. It does not create a value at point C, but it does create an output at D. So, which means it should have an input here. So based on this truth table, let us look into the next question. The column O in the truth table shows the desired output values of the circuit. On figure 2.1, complete the circuit to achieve these output values. So you're supposed to label any gate used. So we have already done this part, and now we are going to use these set of values to get the to complete this diagram. So what sort of a diagram should it be? So it has to be So it has to be a no gate there, so that we get these values here. So let us see. So it has no values at point C and D, so it is creating an output. But in the next two situations, as you can see, it has a value input value, and and here. So if it is having at any point, if it is having any inputs, but if it is not creating an output, that means it is definitely going to be a no gate. Now, when we talk about the third question says figure 3.1 is a circuit diagram. You're supposed to state the names of the circuit components A, B, and C. So A, it is going to be a fixed resistor. It is recommended not just write resistor. Fixed resistor is fine, because the resistance of such resistors is going to be constant. So better refer to it as a fixed resistor. And component B here, as you can see, this is a thermistor. So thermistor, it fluctuates its resistance based on the temperature. And here we have a diode, but since we have these arrows, it is what we say is the light emitting diode. We call that the LED. Now, when we look into the next part of the question, it says the circuit can be used to indicate a change in temperature. State and explain what would be observed when temperature changes from hot to cold. So how actually does a thermistor work? You should understand a thermistor is a temperature dependent resistor. So its temperature based, if the temperature changes, if it is increasing or decreasing, it changes its resistance. If the temperature is increasing, always remember that the resistance will be decreasing. And then if the temperature is decreasing, and that the resistance will increase. Please keep this in your mind. And how does this circuit work actually? What happens is, so current flows like this, it goes, and then what happens is, if the resistance of this section, if it is higher, then the current will opt to flow like this. Current will always opt to flow in a pathway where it is experiencing the least resistance. So if the resistance of this region, if it is higher, then it will go like this. So if it is going like this, then the LED will be lighting up. And then what happens, if the resistance of this section, if it is reduced, and then if it is lesser than this pathway, then current will opt to flow like this. That means the LED will not get sufficient amount of electricity, so that it cannot glow there. That is how this circuit works. So explain what happens when the temperature changes from hot to cold. So it is getting colder. So the temperature is decreasing. That means the resistance should be increasing. So what happens? The resistance of this section, it is increasing. That means current will opt to flow like this. That is your explanation. And what happens? The LED will light up. Okay, so that is your answer and your explanation. Because the temperature is decreasing, the resistance is increasing. So the current will flow in the alternative pathway which lights up the LED. That is going to be your answer. When we look into question number 4, the question number 4 says the resistance of a circuit component varies with brightness of the light falling onto the surface. State the name of the component. So it is a light dependent resistor, which is LDR. A resistor which depends on light. Previously, we just studied about a resistor which depends on temperature. Okay, and the question says draw a circuit symbol for this one. So it's a light dependent resistor. It has to be a resistor with arrows indicating that light is falling into it. So when we go to the next part, it says figure 4.1 shows a 6-volt battery connected in series with a 1.2 kilo ohm resistor and a thermistor. At a certain temperature, the resistance of the thermistor is 2.4 kilo ohms. Calculate the reading on the voltmeter. So there are multiple ways which we can do this. So I'll first explain the calculation part there. So according to the question here, it is 2.4 kilo ohms. But remember, when you're doing the calculation, the unit here, it's not in its SI unit. So you have to convert it into ohms. First, we'll have to find the current in this circuit. And as we know that this is a series circuit, so in a series circuit, the current will be constant throughout. So if it is here, or here, or here, or here, current will remain the same. So let us first find the combined resistance. So the combined resistance will be 1.2 plus 2.4, which is 3.6. This will be kilo ohms, and then if we convert this would be 3600 ohms. So current is equal to V over R. It is 6 divided by 3600. So the answer we get after rounding off 0.00117 amperes. This is the current throughout. Now, since we know the current, and then here we already know the resistance, we can find the voltage there, the potential difference there. So which means V equals IR, and the current value is 0.0017, and then it is 2400. Please don't write 2.5 because this is 2.5 kilo ohms. So the answer you should get, it should be after rounding off, you'll get the value as 4. So I did explain, I just explained the calculation part. Now there is a direct method that you can opt. Now what happens here is the resistance values here, one here it is 2.4, the other one is double of that, which is 2.4, 1.2 and a 2.4. So how does the potential difference is divided here? It's based on if the values here, if it is constant, I mean, if the values for both the resistors are equal, then the potential difference will be divided in a 1:1 ratio. But in this scenario, it is 1:2 ratio. So what you need to keep in your mind is that if the value here you get here, the value you get here, V value you get here, it should be double here. The voltage value you get for the thermistor should be double that, because the resistance is doubled there. So which means if you are getting a 4 here, you should get a 2 here, because it should be half the value here. So same way you can go the other way around. So only this combination of 2 and 4 will give you this ratio and the total of 6 volts there. So I hope you understand this. You'll need to practice a couple of more questions on your own without the assistance of anyone so that you can be more confident on this. So that concludes all the questions for today. We have thoroughly done a couple of questions on both the topics of logic gates and circuit components. I want to make sure that you understand what you need to know in these topics. So the first one is you need to know all the logic gates and its truth tables. You need to know that. And then you need to know the combination of all of the gates, maybe a couple or maybe 3 gates combined together. What are the outputs? You need to draw the truth table. You might have to draw the truth table for that as well. So you need to practice combined gate questions as well. And then you need to know all the circuit components. It's a must to know, and you should know the functions of each and every component, how it works, and based on the scenarios, what changes is it bringing, and how the changes are brought. I mean, if a change is there, maybe an input change is there, and what difference does it bring into the circuit which it is connected. So that is all for today. Thank you very much, dear students. I hope you understood today's lesson. Thank you very much, and wassalamu alaikum wa rahmatullahi wa barakatuh. I hope you understood today's lesson. Thank you very much, and wassalamu alaikum wa rahmatullahi wa barakatuh.